Okay, so here's where we are. We talked about general properties of black holes last time, and Bekenstein-Hawking entropy in particular, the generalized second law, entropy, matter entropy lost into a black hole is somehow made up for by the black hole entropy itself, and so a second law in its generalized form is upheld. And we talked about how this leads to universal bounds on the entropy of matter. It would seem to lead to universal bounds on the entropy of matter, since the black hole doesn't care very much about what it swallows and whether that's made up of quarks or strings or whatever the fundamental degrees of freedom are. It seems like we don't need to know that to bound the maximum entropy that can be in a region of space. And we saw that just from considering black holes alone, we cannot derive a universal bound, but there does seem to be one that exists, the covariant entropy bound. And it suggests that there is some universal relation between area of surfaces and the information content of space-time, the holographic principle. Okay, so today I'm going to go to part 2. and to the extent that I talked about entropy last time, I'll be talking about information this time. And remember, the relation is pretty simple. If curly n is the number of dimensions of your Hilbert space, you can either have a lot of information if you know the quantum state, or you can have a lot of ignorance if you don't know it. These two concepts are very closely related. Okay, so I'm going to start with Hawking radiation, and especially in light of the firewall controversy that's erupted over the last few months, I think that's really brought home what a profound insight Hawking radiation was, and how it's led to difficulties over more than 40 years, or well, sorry, almost 40 years, that we still have not, probably not even come close to resolving. Okay, so how did Hawking find out that black holes radiate? First of all, it's worth noting that in flat space-time and Minkowski space, there are basically two ways of defining the vacuum. In a quantum field theory textbook, you might find it defined like this. It's the state from which no particles can be removed, so it's annihilated by all the annihilation operators to 0. It's, of course, also the state of lowest energy. And these annihilation operators are defined by decomposing the quantum field into some set of modes, these kind of modes that you've seen on page 2 of the quantum field theory textbook. And they come with what's called positive frequency, which is the case where there's a minus sign here for some bizarre reason, and negative frequency, which are the complex conjugates. And the coefficients in front of them are the things that you quantize and impose commutation relations on. And then the guys in front of the positive frequency modes are the annihilation operators. That's also absurd, but that's the convention. Now, in curved space-time, there is not necessarily any notion of energy, certainly not of total energy. And so there's no invariant notion of positive and negative frequency. You'd need a preferred time coordinate to have that notion. In fact, it turns out that even in Minkowski space, you can define perverse time coordinates where you get a different decomposition. But certainly in curved space, you wouldn't necessarily even know how to start if you don't have any special symmetries, any killing vector fields, or anything like that. What you still can do, and this is how people do quantum field theory in curved space, is you pick some decomposition into modes with well, you wouldn't necessarily say positive or negative frequency. There may not exist a time coordinate with respect to which that's true, but they can have positive or negative norm. In Minkowski space, those two concepts coincide with each other. Remember that the norm is defined by something like that, and the negative frequency modes have negative norm, -1, and positive has +1. But what's happening now is that there is no unique way of doing this decomposition. So there's, depending on what complete set of modes you pick that you can build any field configuration out of by linear combination. You can pick different bases, different mode sets, and they will lead to a different subspace of positive norm modes. Okay, and so there's some randomness involved there. Okay. Now there are situations where it's not completely random, and that's one where that's the one that Hawking considered is such a situation. If you have a space-time which is just basically Minkowski space at early times, and then you bring some matter in from far away and you collapse it to form a black hole. So now there's an intermediate region where space-time is curved. But you can go far from that region, and at that distant region at late times, again, you would expect that there's a preferred way of decomposing the quantum field. Okay. So there are these three different kinds of regions, sort of an early, late, and some interaction region in between where space-time is curved. And so what you have is a situation where at early and at late times you have a preferred way of defining your vacuum. But in the middle you don't. And the interesting, surprising, non-trivial thing that Hawking discovered is that in that case, it need not be true that the vacuum state that you define, the preferred state that's defined at early times, is actually the same state in the Heisenberg sense of evolving it into the future as the vacuum state that's defined at the late time. So just to make that completely clear, the situation we're going to have is you have a sense of what the vacuum is at early times. You evolve that exact state into the future, and then you compare it to what you would consider the vacuum state at late times, defined in the natural mode decomposition at late times. And you find those two are not the same state. So in fact, from the viewpoint of an observer at late times, particles have been created, even though there weren't any there at early times. Is that clear? We'll go through this in some detail, but so here's the setup. We consider a black hole that's formed by collapse. One of the main subtleties that Hawking had to deal with is to what extent the complications from the actual collapse part of this story, where the matter sits that formed the black hole, to what extent they affect his calculation, and he has very smart arguments about why they don't affect it. And I'll have to sort of skip over that in this summary. But yeah, so at early times, we've just got empty flat space, and then we bring some shell of stuff in from far away, and you get this usual mode decomposition, and then we've got an equation of motion that tells us how to evolve this vacuum state that's defined with respect to these modes forward in time. Now, I should draw some pictures at this point. Maybe it's okay to erase this now, organizers? Okay, so I hope you all remember the Penrose diagram of the black hole. Okay, so here's some star that collapsed. Okay, and this is just vacuum, and so here there's some early time slice, in which we have the usual vacuum state defined. Again, up to this matter here, but that kind of factors out. And the radiation doesn't come from this matter. Okay, so we don't have to worry about the matter. And then at late times, so really you can really think of defining the initial state right here on what's called scry minus or past null infinity. At late times, we can again ask, okay, where, what is the Cauchy evolution leading us to at late times? And you might say, okay, well, there's again a Cauchy surface right here and just underneath the singularity. So those two things put together would be a Cauchy surface where if I specify the data, I know everything. But of course, equally well, I can say that this is a Cauchy surface. Right, the horizon of the black hole and future null infinity. And so they together form a Cauchy surface, but now if I want to set up a complete set of modes so that I can write any field configuration as a linear combination of them, basically what I have to do is I have to take modes with support here, and there'll be positive and negative frequencies coming with those, and another set of modes with support over there on the event horizon. I mean, in the physical space-time, even though they meet here at this corner, the event horizon of the black hole and future infinitely large radius, which is what this is, are far away from each other. So you have to have two mode sets, basically one which captures all the stuff that falls into the black hole, and one that captures all the stuff that doesn't. Okay, so in physical space, it'd be something like this. There's all the stuff that falls into the black hole, and there's just stuff that makes it out. Okay. So that's why you have four terms now. Okay, the PIs are modes associated with future infinity out here, and the BIs are the associated creation and annihilation operators, and then the QIs and CIs are the same things for things that cross into the black hole. Now, of course, the AIs and FIs, the usual mode decomposition that I did down here, and this decomposition that I just wrote down, they're not independent of each other because I can use the equations of motion to evolve any mode function into the other. So, for example, I can write the PI modes as some linear combination of the Fs, but notice that in order to do that, in general, I will need to use both the positive and the frequency and the negative frequency modes in order to build up one of these PI mode functions. And then correspondingly, the associated operator is constructed as a linear combination of annihilation and creation operators. So an annihilation operator with respect to the natural mode decomposition at late times is a linear combination of annihilation and creation operators. And that's important. This mixing is crucial. It doesn't always happen, of course, but it happens in this space-time, and that's what led to Hawking radiation. So again, the initial state we're going to say is just a vacuum. There are no after the black hole forms, we're going to let no more particles come in. And because of this mixing, this vacuum, which is annihilated by the AIs, will not be annihilated by the BIs, because the BIs contain an AI creation operator, an AI dagger in them. Okay. And so you can compute things like the expected occupation number at late times, and it's related to this beta part of the Bogoliubov transformation, the admixture of creation operators. Okay, so you need to compute this thing to compute Hawking radiation. That's all there is to it. Well, there's a small complication which has to do with the fact that first of all, of course, it's not a sum. It's an integral because we've got continuous frequencies. But then this occupation number is really infinite. That has to do with the fact that if you don't, suppose you know the answer already. Okay, the black hole radiates. Well, if you just sit here, it's going to radiate and radiate and radiate forever. If you don't include back reaction, if you don't include the fact that this actually is going to make the black hole smaller and it's eventually going to disappear. And so you get the answer infinity if you forget about that, but you can handle this by defining wave packets. So instead of dealing with modes that are essentially defined over an infinite amount of time, you deal with wave packets, and so Hawking goes through that as well. I'm really following his paper very closely, by the way, in this summary. I'm skipping a lot, but in terms of the basic formalism, the way he went about it is really, even the notation is pretty much what he used. So what do you finally get for this expected occupation number once you go over to wave packets? You made it even more complicated. Well, in fact, the final result is very simple. Hawking defines something which has a natural interpretation as the absorption probability for a wave packet. It's Well, again, it's the probability that that wave packet, if you time reversed it and threw it into the black hole, would actually go into the black hole as opposed to just somehow scatter off of it and go back out. That probability, for example, would be very close to 1 if you had a wave packet which was much smaller than the black hole in size. Then of course it's going to go in. But for example, for wave packets which are very large in size compared to the black hole, there's a relatively small probability of absorption. So that's just some quantity you can define. And the key result is that the emission probability is related to the absorption probability by this factor, or more precisely, the expected occupation number for this mode is related by this factor, which is thermal emission. Okay, it's thermal emission with a temperature given by the surface gravity over 2 pi. Okay. So that's the key result. The black hole acts as if it was a thermal body with temperature essentially given by the surface gravity. And to really show that it's thermal emission, of course, you need to do more than just check that the expected occupation number of every mode is the one that you would get from thermal emission. You really have to show that the probability for every particular state that might come out of the black hole is precisely given by the Boltzmann formula. And if H is the Hamiltonian here, or the energy, you want to see that the state coming out of the black hole is a thermal state in this sense. It's a thermal density matrix. And Hawking showed that as well 2 years later in 1976. He probably knew it, but it was made more explicit then. Okay, so it's really thermal radiation. Now, notice thermal radiation, again, it means that there's a density matrix. It's a mixed state. It's not a pure state. There's a different probability for various different states. Probability really in the classical sense, like you don't know which one it is, could be anyone. So this leads to the information paradox. Before I go there, any questions? Okay, so onward to that. So here is the abstract. This was a little later, came out in '76. And notice that the first words here are the principle of equivalence. And we're going to encounter this again. This war between information lost and information not lost, the war between firewalls and no firewalls, comes down to a war between the equivalence principle and the principle of unitarity. The principle that underlies general relativity and the principle that underlies quantum mechanics. And we're really seeing them coming to a very sharp collision in this setting, and that's what makes this so interesting and exciting. The principle of equivalence tells us that, well, gravity is attractive, together with positive energy. It leads to singularities. And really what Hawking is saying seems on the face of it completely obvious. This star here has some information in it. It could be in some particular quantum state psi, pure state. And now we know, okay, there's Hawking radiation coming out of the black hole. But it's not terribly surprising that we should be losing information, because the information about which quantum state this was went over here into the black hole and presumably somehow crashed into the singularity, and now it's gone. And what we're looking at over here from the point of view of an observer at late times at large distances is just some subset of the original degrees of freedom. And in fact, all of the important degrees of freedom, the ones that carried this information, went into the black hole. If you draw a slice here, you don't have access to all of space. You have access only to a part of it at late times. You're not receiving signals from here. You can't probe this region. If you lower a probe into the black hole and you try to pull it back out, you're out of luck. So you really have no access to the interior of the black hole. From that viewpoint, Hawking's result is extremely natural. Stuff went in there and went away. Can't go there. It's gone. So he concludes that the interaction region in this case has what he calls a hidden surface, which you can think of as any time slice that lives entirely inside the black hole. For example, something near the singularity or the horizon. And that we don't have access. You have only limited information about this hidden surface, basically just the conserved charges, mass, angular momentum, electric charge. And that this hidden surface emits with equal probability, where is it? All configurations of particles compatible with the observer's limited knowledge. And so the final situation is represented by a density matrix rather than a pure quantum state. That was, of course, a revolutionary claim because he was saying that basically from the viewpoint of somebody doing a scattering experiment, you sit out in infinity. I mean, you can do this at CERN if they had a little more energy. You throw stuff in, you wait for mass to come back out, and there should have been a unitary S matrix that relates those two things to each other. And what he's saying is, no, there's not. If you form a black hole in the middle, then there is no unitary relation anymore. And in fact, what comes out is unrelated to what you threw in. It's always the same probability distribution over many different possible pure states. So why didn't people believe this? There was, of course, an uproar. I'm not sure how big the uproar, maybe some of the people who are old enough to remember this could tell me. I don't know how big the uproar was in the 70s. Did you care, Eliezer?
I was the student who didn't care about it.
He didn't care about it, yeah.
Very cared.
Did he care about it in the 70s? Because I've never asked him, because I don't think he published on it in the 70s. I mean, even this paper with Peskin and Banks was later. So I do think it somehow took a while for, maybe people just didn't take it seriously or didn't realize that they had to take it seriously. I have no idea. But once people did take it seriously, then there was this very interesting sociological division into people who grew up learning general relativity and people who grew up being particle physicists. The GR people were like, well, of course you lose information for this reason I just explained. It goes into the black hole. What's the big deal? To a particle physicist, it's an abomination, right? You have an S matrix. Who cares if there are black holes appearing in the path integral? You're really just doing it doesn't even make sense to say that there's definitely a black hole there, right? Even in a limit where the black hole is almost certainly there, like it's a big classical thing, it's always still a path integral that you're doing to compute some S matrix. How can it possibly be that this S matrix is not unitary if it is in particle physics, just because we've included gravity? And how could such a violation of a basic principle not sort of spill over? And this is, in fact, what some people like Banks and Peskin and Susskind argued, that you can't violate unitarity a little bit in the weak gravity limit, the same way that you can't be a little bit pregnant, that you would have a very major disaster in physics if you allow any violations of unitarity. I'm not sure how convincing those arguments really were, but here's another one. Here's another one for why Hawking had to be wrong, which I guess couldn't have been given then. But now that we realize that there are these non-trivial entropy bounds, that they at least seem to survive a lot of non-trivial challenges, so maybe there's good evidence that they're correct. It would be truly ironic that a black hole has enough entropy to store the information about what goes in. I mean, that's what these entropy bounds say, right? The entropy of the matter that goes into the black hole is less than the Bekenstein-Hawking entropy of the black hole. In fact, that's just what the generalized second law says. So the black hole has enough entropy to store the information about what goes in, and yet Hawking is telling us that in the end, when the black hole evaporates and converts itself back into matter, it loses that information anyway. Kind of bizarre. Okay, neither of these arguments are particularly convincing. One that I find a little bit better, before I get to the really convincing one, is one that for some reason was not given by anybody, as far as I know. But they could have been obtained by simply adapting that famous first paragraph in Bekenstein's paper that I showed you. After all, remember, Bekenstein did something pretty crazy. He said that it bothered him that entropy, that ignorance, can be lost into a black hole, that you could destroy entropy, violate the second law for all practical purposes by dropping entropy into a black hole. And he said, well, we can't have that. We have to assign, an entropy to the black hole horizon in order to make up for that. And that was really a pretty radical viewpoint, because he could also just have said, well, of course entropy goes into a black hole. Here it is. We haven't really destroyed it. It's just that you can't get to it from the outside. But then, the whole black hole thermodynamics story came together. Hawking discovered his radiation. Bekenstein was vindicated. This argument actually won the day. But it would be completely crazy if you could destroy entropy by throwing it into, if we find in the end that you can't destroy entropy by throwing it into a black hole, but you can throw in information, which is essentially the same thing, that's the flip side of the same coin, by throwing that into a black hole. Or think of replacing entropy with information in this sentence on every occurrence, and second law of thermodynamics with unitarity. Okay, and then just read the sentence again. And we would, in the end, we would say the outside observer cannot exclude the possibility that unitarity may have been violated in this process. If it bothered us that the second law, that the outside observer can't verify whether the second law still holds, it should bother us equally much that the outside observer can't verify if unitarity still holds. In both cases, it's the same problem. We can't really get into the black hole to see where this stuff allegedly still is residing. Okay, so that to me seems like a pretty good argument. If this argument was wrong, it should have already shown up at the level of entropy, and it didn't. Of course, the real reason why most of us, including Hawking apparently, now believe that information is not lost is the ADS-CFT correspondence. So there we have a complete definition of quantum gravity in a certain class of spacetimes. The formation and evaporation of black holes is certainly one thing that can happen in those spacetimes. It doesn't matter too much that they're anti-de Sitter space on large scales, because you can consider a limit where the curvature radius of ADS is very large, and you make comparatively small but still large black holes in the center of the spacetime and let those evaporate. The whole thing is described, or at least there's overwhelming evidence that it is correctly described by a completely unitary quantum field theory, conformal field theory, where there's just no room for information to be lost. There's no gravity in there. You can put it on a computer. So that's, again, I mean, you can even question that, and some people do. Maybe the correspondence isn't completely exact. Maybe the CFT does not describe the formation and evaporation of small black holes in anti-de Sitter space. But I think that's really a rather contrived viewpoint, given all the evidence. So suppose we buy for a minute that information loss can't possibly be true. Unitarity must be upheld. Then we have to ask ourselves, where did Hawking go wrong? And actually, before I go there, maybe, let's see, when did I start? 2:30? Okay, yeah, good. So we have lots of time. Got confused. Good. So where could Hawking possibly have gone wrong? And that has been one of the most frustrating things for people to try to figure out. Because, in the beginning, it seems like maybe there are a few places in the calculation where he's stretching the regime of validity of what he's doing. Actually, no. And you can clean those up, and there is no. It's pretty much unassailable in the sense that he played by the rules of the game as they were defined. You're going to have to change the rules of the game to say that something was wrong with Hawking's calculation. He basically just assumes the equivalence principle. He assumes that the infalling observer sees nothing special at the horizon. The horizon is a harmless place on scales that are shorter than a Schwarzschild radius. It's just empty space. That's the starting point for the calculation. And then the method is quantum field theory on a fixed background, spacetime, the Schwarzschild background. And again, that seems completely legitimate. This is the sort of thing that should work as long as we stay away from places where the curvatures become of order the Planck scale. And we're staying away. The calculation makes no reference to this region here, near the singularity. It makes reference only to the region near the horizon and out. And we can make the black hole as large as you want, make it, 10 million light years across. It's a harmless place, no curvature at the horizon. So, in that sense, the calculation is clearly correct. So something has to be wrong about our assumption about when these things are valid. Well, maybe not. Maybe there's one more way out that I should mention first, and then dismiss, called remnants. After all, what happens when the black hole radiates, and I guess I didn't actually say this, but you can just check using Boltzmann's law and the temperature, which remember is basically 1 over the Schwarzschild radius. How long does it take for the black hole to evaporate? So it emits mass. There's some back reaction. The black hole is getting smaller and smaller. You find that the time scale for evaporation is the initial Schwarzschild radius cubed. So the black hole is very, very, this is in Planck units, right? So that's, I guess, a time scale. So it's huge for a solar mass black hole. It's much larger than the age of the universe. But of course, towards the end, first of all, the thing gets hotter and hotter because the radius of the black hole is getting smaller. And then eventually you get to a point where the black hole has Planck size. And the temperature goes Planckian, and the curvature scale at the horizon is Planckian, and you don't have any control. Now, this is a runaway process where the thing is radiating faster and faster, and then as it gets to this point, the natural assumption would be that it's not like things are tapering off as you get to that point, so that you would maybe conjecture that the evaporation process stops as the black hole gets small. It's exploding in the end. Nevertheless, some people thought about the notion that there could be a remnant, that in the end a little Planck-size piece or particle or tiny black hole, the distinction would be hard to make, remains behind. And even though no information came out all along while Hawking radiation was coming out, this Planck-sized remnant carries, in fact, the information. And if you take all the Hawking radiation and put it together with this remnant, you once again have a pure state, the original pure state in the Heisenberg picture that you sent in. This is a very ugly possibility, and almost certainly wrong, because it would mean that an object of a particular mass, the Planck mass, can carry an arbitrarily large amount of information, or has an arbitrarily large Hilbert space associated with it. Because after all, there's no limit to how big I could have made the black hole to start with. It'll always evaporate down to the Planck size, and then that little thing has to carry, again, an arbitrarily large amount of information. That would seem to lead to instabilities. There's just too much of an amplitude to produce these things. No matter how suppressed tunneling into Planck remnants is, you have an infinite phase space to multiply it with. So you're going to just, why doesn't this table become remnants? Another reason why I don't like them is they conflict with holographic entropy bounds. They completely fly in the face of all other experience we have in terms of these bounds actually being satisfied. You can't have arbitrarily large amounts of information in small regions of space. So what else could have gone wrong? Well, informed, I guess, by this holographic principle idea, there is, in fact, something that could have gone wrong here. As I mentioned, the process takes a very long time, and the number of quanta emitted, there's basically one Hawking quantum per Schwarzschild radius time, so Schwarzschild radius divided by the speed of light, that's getting emitted. Their overall RS squared, or quanta, being emitted. Basically, the number of quanta is roughly the area of the original black hole in Planck units. And that's a lot of quanta coming from a region of space that was only that large in area. Okay, that's precisely the number of quanta that corresponds to the holographic entropy bound on the amount of information you could have had in this region. And remember that this holographic entropy bound conflicts at a fundamental level with local quantum field theory. It tells us that all these degrees of freedom that quantum field theory would seem to have there for us, even if you put some short distance cutoff, it should scale like the volume. The number of degrees of freedom in this region should have been RS cubed. But the holographic principle tells us that secretly, that's overcounting. There's some huge redundancy in quantum field theory that we don't see if we just probe a few of these degrees of freedom all at the same time, and that gives us this illusion of locality. But fundamentally, all those volumes worth of degrees of freedom are not there. More than RS squared degrees of freedom are not there in a region of size, of area RS squared. And at the end of the day, when we follow Hawking radiation through, some order 1 fraction of the evaporation process, we're getting in a situation where the number of quanta that have been emitted becomes comparable to the holographic entropy bound on the region that they're coming from. So just at the sort of vague level, that could induce in us a suspicion that perhaps what's breaking down is quantum field theory, not in the sense that, we're going past some cutoff in the usual sense where we're using it at energy scales where it's not valid, but in the sense that there's got to be some way in which quantum field theory is wrong if you appeal to too many independent degrees of freedom in a given region of space, and that seems to be what's happening here. You may notice that this is really weak, right? It's not like we're pinpointing something. Over here, we know exactly how to do it better, and how to correct this mistake. The best thing that I can come up with is some vague notion about how maybe the holographic principle is being violated in this calculation, but we don't have anything to replace it with. Right? And the arguments from ADS-CFT are very indirect. They don't give you a way of computing in the bulk what Hawking should have done instead. So, nevertheless, given the evidence from ADS-CFT, I want to ask, well, suppose that information is not lost. Suppose that there was something wrong in Hawking's calculation. Can we at least understand whether the starting point of Hawking's calculation isn't already completely in conflict with the idea that the information comes out? The starting point being the equivalence principle, that an infalling observer sees nothing special at the horizon. And the beauty of the firewall argument that I'll get to in a little bit is that it's telling us that the answer to this question is essentially no. Right? The conflict is really very sharp. It seems very difficult to reconcile unitarity with the equivalence principle, even if you wave your hands and say holographic principle. But I'm not going to say that yet. I'll give you a little bit of the prehistory because, in fact, a lot of things seem to point in a direction that this is possible and that a bunch of miracles happen that make this possible. So let me go through that. So again, just to make completely clear, the equivalence principle means that in the vacuum on curvature scale, on distance scales much less than the characteristic curvature scales, an observer should be able to describe local space-time to a very good approximation as Minkowski space. An example is an observer who is crossing into a black hole a little while after the black hole settled down. They should see nothing but vacuum right here at the horizon. The horizon should be a completely harmless place. We could be entering a black hole right now and not know anything about it, as long as the black hole is very much larger than us. Okay. In fact, to some extent, you can't even by causality, you cannot know when you're entering a black hole, because consider a black hole that's formed by a null shell that's collapsing like this. So this is, a shell collapsing, and you're sitting here. Right? The shell is actually in your future, or space-like related to you. You can't even see it, and you're already in a black hole at this point, because the event horizon is not causally defined. It's defined in terms of what happens later. So the horizon should not be a special place. So the question is whether we can make that consistent with the information coming back out. And intuitively, you might see that that could be hard, because if the horizon is not a special place, well, how is the information going to get stuck here and come out? So black hole complementarity tried to make that work. And I'll argue later that it doesn't help with firewalls, at least it's not enough. But it did help with a bunch of other apparent problems. And the basic idea of black hole complementarity is that you have to be very operational in the way that you ask your questions or formulate alleged paradoxes in the sense that it's not okay to say, well, there's some contradiction with quantum mechanics in this space-time if I assume both equivalence principle and unitarity. What's important is that whether anybody can actually verify that contradiction. And what would not be okay is if, for that purpose, you have to measure something here and here. Right? Because there's nobody, by causality, there's nobody who can collect information from those 2 points who actually lives in the space-time. You can be outside the black hole and see this thing, or you can be inside and see that thing, but you can't see both. And that's a key idea behind black hole complementarity. So let me give you some examples. Any questions at this point? Kelly.
What does Stephen say about it? Does he finally explain what he thought the amount would be?
I have no idea. I really don't. I didn't find his concession to be particularly convincing. And you know, it's easy to say now that he really should have stuck to his guns. It's you know, I think it's not settled, and but I don't know what he, you know, I haven't discussed it with him.
Mentioned that in the ADS-CFT argument, which is related to Hawking's concession, the argument was that you have to take into account processes where topology changes, and that we are talking anyhow about very small effects. It's very important conceptually, but calculationally the effects are very small, and therefore topology change could, let's say, punch the hole in Hawking's argument, and I think to that he conceded.
Yeah,
that you can calculate exactly and show that everything works okay, but it punches a hole in the argument.
Well, I think it would seem that way, and the firewall argument really shows that this is not sufficient. But yeah, let's see if you'll agree with that. Good. So let me start by stating what you might call the principles of black hole complementarity. The red ones are the ones that basically the unitarity for the outside observer. So the guy who's staying at large radius and observing all the Hawking radiation coming out should see a unitary S matrix. And down here, the fourth one is the equivalence principle, that you get to fall into a black hole and see nothing special at the horizon. And then there are two others which are worth stating because we usually make these assumptions in this analysis. One is that effective field theory is valid outside the stretched horizon. I haven't even defined what a stretched horizon is, but it's basically something that's about a Planck length outside of the true event horizon. And the reason is that it plays some role in these games is that if you're at large distances and you're trying to explore the part of space-time that's accessible to you without having to use, quantum gravity, well, imagine you're lowering a probe towards the black hole. And what you find is that the temperature gets higher and higher. Once the probe enters what I called the zone last time, so about one Schwarzschild radius away from, so here's your probe, you're lowering it, bringing it back. When it's sitting here, it's experiencing a certain temperature, which has to do with the fact that it has to accelerate to just stay at constant radius. If you bring it even closer to the black hole, it has an even higher temperature. And finally, the temperature, this is essentially this Unruh temperature. The temperature gets to the Planck temperature. It would diverge, mathematically speaking, at the horizon. But it already reaches the Planck temperature at a distance 1 Planck length from the horizon. And so the stretched horizon sort of marks the end of the world for an outside observer. Right, for all practical purposes, he can say there's a membrane there. It stored the information about the star that collapsed. It's warm, and it emits radiation very slowly, just like a hot piece of coal would emit radiation that eventually returns the quantum state to you. And what we assume is that once we're outside the stretched horizon, effective field theory should be valid at least more than a Planck length away from the viewpoint of the outside observer. Because again, curvature scales are not large, and in this case, even accelerations are not large that you have to explore this region from far away. And so you should just be able to do quantum field theory on this background. So in particular, you can evolve the Hawking quanta from infinity, where you've defined your S matrix, back to the near horizon region. And that's going to be important for the firewall argument. And you expect that to be unitary. Finally, one of the assumptions here is going to be that the black hole Hilbert space has dimension given by the Bekenstein-Hawking entropy. Okay, so those are the principles of black hole complementarity. Now let's see if they are actually mutually compatible. And I'll give you two examples of apparent contradictions between unitarity and the equivalence principle. Those are the ones that are dangerous here, this guy and this guy. First, this membrane story that I just summarized versus free fall. As I just said, if you're far away, a black hole looks to you like any other object. You know, it's like a membrane. It's a warm membrane. It thermalizes stuff that you throw at it and gets a little bit larger when you do that. And then it slowly shrinks and evaporates away. It even has properties like conductivity and, you know, if you drop an electric charge in it, you can watch it disperse in a certain way. It has a tension. It has, you know, it's a thing. From the outside viewpoint, a black hole is like a thing. And from that viewpoint, then you would expect it to behave like any other thing, which is to return information and not lose it. In particular, an outside observer would not ever say that something crosses the horizon. What happens is that the infalling person redshifts and just becomes absorbed by this membrane. But since I've got all my probes and they tell me that there's a very high temperature there because I'm holding them at fixed radius, it looks like there's a high temperature from this acceleration that I need at fixed radius near the horizon. I can understand that as thermalization. So I would say that Alice, who jumped into the black hole, didn't cross the horizon. From my viewpoint, she just got into a really hot place and got thermalized, and the membrane gulped her up and got a little bit bigger, and later it's going to return her as Hawking radiation. So when I tell that story, it's kind of implicit that Alice doesn't see the equivalence principle acting. From my viewpoint, she's entering a place which is quite special. Temperatures diverge there. There's a membrane at the end. She gets crushed. According to Alice, on the other hand, if we want to satisfy principle number 4 of black hole complementarity, the harmless free fall, Alice should be able to cross the horizon with nothing special going on. She can carry, I mean, this could be Alice sitting here on the surface of this star. She can carry a lot of information with her. Nothing special happens at the horizon, so that information can't suddenly get stripped there and returned to Bob. So it just goes in with her. And so Alice would say, well, there's no possible way that Bob out there can get that information. I've got it right here in my pocket. Okay. And so it seems naively that there's a contradiction between these two viewpoints. But in fact, no contradiction can be communicated. Because by the time Alice is inside the black hole with the information in her pocket, she can't write a letter to Bob, who stayed outside, saying, I've got the information. You can't possibly have it too. And conversely, by the time that Bob has concluded that Alice has been thermalized on the membrane, that's essentially the relaxation time or scrambling time scale of a black hole. At that point, it's too late to send a message towards the black hole that could still possibly reach Alice for this reason that we discussed last time. There's an enormous amount of redshift going on between objects that fall into the black hole at different times. And in fact, if they're separated by more than a scrambling time, they can't communicate to each other, even though they're both inside the black hole. Okay, so you're starting to see the pattern here. The idea is that, yes, there are apparent contradictions between unitarity and the equivalence principle, but I can always resolve them by saying, well, those contradictions only become apparent when it's too late to communicate them. Alice, the person who wants to fall into the black hole, they can always fall in, and they can say, yeah, the equivalence principle is working here. And the guy who stays outside can always say, yeah, unitarity is working here, the black hole's like an object. And they'll never be able to get together and argue. And so that's okay. A sharper contradiction, which was analyzed in the early 90s by Susskind and others, is what you get when you actually look at the evolution of this quantum state psi down here, and you assert unitarity and the equivalence principle, both of them. So equivalence principle tells us that my star that's in the quantum state psi just gets forward evolved, but in the Heisenberg picture, it's still in the quantum state psi up here, some distance away from the singularity so that we're under good control, but inside the black hole. Yet I'm also saying that the Hawking radiation that goes out here, that's this green cloud making its way out to future infinity, carries that state. That's when I'm asserting unitarity. The contradiction is that I can draw a time slice across the whole space-time such that both of those instances of the state psi are present at the same time. They're space-like related. Okay, so that's unitarity. That's the equivalence principle. And that's a problem. Okay, what's happened here is that the black hole, it didn't matter what psi was. What the black hole did was convert it into psi cross psi. And that is called quantum Xeroxing. If you can do that for an arbitrary quantum state psi, if you have a machine that does this for you, that machine has to violate the linearity of quantum mechanics, and that's a one-liner. Just consider what that machine would do to the state psi plus phi, right? By linearity, it should take it to psi squared plus phi squared, but it should also take it to this squared. Okay, it can't both be true. So you can't have quantum Xeroxing. This is a well-known theorem that, of course, predates this whole black hole problem. And again, our way out is going to be that there is no observer who can see both copies. This seems kind of obvious in this diagram because there's no past light cone that's actually inside the space-time. Remember, light rays are at 45 degrees. There's no past light cone that contains both copies, so I couldn't possibly communicate anything to a single observer about their joint existence. But in fact, you have to do a calculation to show that this is really so, because, for example, you might worry about the fact that I've got an inside copy present in the black hole, well, immediately after the star crosses the horizon. And so why don't I measure a bit in the Hawking radiation early on when it starts coming out, and then arrange to have that same bit sent to me when I jump into the black hole right away after measuring that first bit of data in the Hawking radiation. It seems like, you know, I could come up with clever ways of, in fact, observing Xeroxing. And that's precisely the strategy that Susskind and Thorlacius analyzed. So Alice falls in with a star. She's, you know, made a plan with Bob all along that she was going to extract a particular bit of information, the one that Bob's unitary S matrix tells him is the first one to come out in the Hawking radiation. Bob waits for that bit to come out, then quickly jumps into the black hole. Alice has packaged her bit into a message and coherently sent it to Bob. Now Bob has both copies in his hand. Inside the black hole, but who cares? Now we've got a single observer, Bob, who holds both copies. Quantum Xeroxing has happened. But you can't do it, and you can't do it for the following reason. Remember that such communication is only possible if Bob and Alice fall into the black hole separated by less than the scrambling time scale, RS log RS. If they're separated by more than that, then any information that's sent by Alice up that way will be too redshifted for Bob to be able to decode it before he gets to the singularity. It will not, in fact, fully reach Bob by the time he gets to the singularity. Bob has only a finite time. You can't prolong the time that you have until you hit the singularity. It's of order Schwarzschild radius or less. Now, how much is the separation between Alice and Bob's infall time? In fact, it's much larger than the scrambling time, RS log RS. Sorry that I'm using capital R for the Schwarzschild radius here. Different notation. It's much larger. It's actually of order Schwarzschild radius cubed for the reason of a theorem by Page that I'll have an opportunity to go into more detail about later. But let me just tell you the upshot. If the Hawking radiation is coming out, well, let's say you have a piece of coal that is in a pure state and evaporates. Okay. How long is it going to, how much of the smoke do you have to look at before you get to extract at least one bit of information from this smoke? Well, you might think that it's some fraction of, that corresponds to how much of the black hole is, of the coal, has evaporated. And it just goes up linearly with the amount that's evaporated. So this is how much coal is left. This is how much information I've got in the smoke. The coal is just converting itself into smoke. Right? Here the information is in the coal. Here it's in the smoke. But in fact, it's not so. The real curve looks like this. You get no information at all in a typical quantum state for the coal. You get no information at all until the halfway point, until half of the degrees of freedom are accessible to you in the form of smoke. And then the slope is twice as steep as you would have naively thought, and in the end you have all the information when the coal is gone. Okay. That's what actually happens in a typical quantum state. And the reason for that is the typical quantum states are very highly entangled. Okay, so they're basically versions of this Bell state. Right. Where if I hold, so here I have 2 bits, right? If I have half of that, which corresponds to this point, I have no information, right? One of these bits is actually in a completely mixed density matrix. It could be 0, it could be 1. What I measure doesn't tell me anything about the quantum state. I would just destroy the quantum state by measuring it. What I'm trying to recover, after all, is this quantum state. I need both of the bits to recover that. So for systems with more than 2 qubits, the answer is more complicated, but it's given by this curve. You get nothing until you have at least half of the qubits in your hand for a typical quantum state. Typical means very entangled. So that means that Bob has to wait for essentially half the evaporation time to get his first bit out. And only then can he jump in. And so we're dealing with r cubed versus r log r. It takes much too long. You don't even come close to verifying Xeroxing here. It's maybe a little suspicious how much you fail, by how much you fail. And in fact, later on, Hayden and Preskill discovered a smarter strategy for trying to verify quantum Xeroxing. And in their strategy, it turns out that you can get as close as the scrambling timescale. So you're just barely unable to argue that somebody can see quantum Xeroxing, which is in a way more satisfying. It seems like there's a kind of conspiracy against it. It seems like this complementarity idea really works. These apparent contradictions between the equivalence principle and unitarity really are resolved by taking an operational viewpoint and asking, well, can anybody actually see this contradiction? No? Great. Okay, so the summary here is, okay, we have apparent contradictions between these 2 things. And secretly, we've been assuming something else, which is that we get to play God and look at the space-time from the outside and see what's inside the black hole as well as what's in the Hawking radiation. And it's that hidden assumption that we have to give up. And then everything's fine. Okay, so that's complementarity. Now, if this is the right conclusion, if this is what black holes force us to do, it's quite far-reaching in a way. If we don't get to play God, if we don't get to talk about a space-time in its entirety, if we have to pay attention to what can be accessed by a single observer, then presumably that's some deep insight that is not just confined to the context of black holes, but that we would have to keep in mind in situations whenever the causal structure of the space-time is non-trivial, so that there doesn't exist a single observer who can see everything like in Minkowski space. It would seem that we have to keep that in mind. So cosmology is a great example, in particular de Sitter space, which is what we're heading towards. There are horizons. Maybe we shouldn't think of de Sitter space globally. This is why I answered a question last time in terms of the causal patch. It's precisely because of this. And in fact, applications of this idea of observer complementarity to cosmology seem to help enormously with what I consider the deepest problem in cosmology, which is the measure problem, the fact that in a large class of universes, it seems like there are infinities popping up all over the place that prevent you from computing probabilities, in particular in de Sitter space and related spacetimes. So if you restrict to a single observer, those problems seem to go away, and you seem to get well-defined probabilities, which even give you good agreement with observation for questions where you know how to compute that. But you have to try to be specific about what this actually means in a general space-time. What does it mean to restrict to what a single observer can see? Well, the idea is that you restrict to a causal diamond. So a single observer, of course, we don't want to have practical limitations coming into this, like the fact that we all die. Okay, that's too bad, but it has nothing to do with the fundamental laws of physics. And so we're going to give the observer as much time as they could possibly have, which is, you know, maybe between the Big Bang and some kind of crunch. And so, you know, you consider a maximally extended world line. You make it as long as you can make it, and you ask, okay, what can that observer probe? And what that observer can probe is stuff that's both in the future of the starting point and in the past of the end point of their world line. Right? And so more generally, if you have two observations and you have some contradiction between them, what you're going to test for is, does there exist or does there not exist such a world line or such a pair of points which are causally related to each other, such that both of these contradictory experiments take place within what that one observer can probe. And what you're going to hope to find is that there does not exist any causal diamond that contains both contradictory experiments. That will be the generalization of this morale of the story to arbitrary spacetimes. Okay, so what complementarity says is, there has to be a consistent theory that describes all the experiments that the infalling observer can make. There has to be a consistent theory for the outside observer. They have to agree on things that they can both measure and communicate to each other about. Stuff that, gets measured back here before the black hole even forms. Or even here, when Alice, who's jumping into the black hole, could still decide to turn around and go out and become Bob. At that point, the experiments really do have to, their descriptions, their theories have to agree with each other. But it's perfectly okay for Bob to say that Alice gets fried at the membrane, and for Alice to say that Bob loses information because she took it with her, if each of them say this at a point when they can't tell the other guy about it. Then I think we're allowed to be happy. Okay. So complementarity resolves the two apparent paradoxes that I've described. One guy says there's a membrane there. Alice falls in. There's no membrane, and so on. There's a quantum Xeroxing problem. But recently, a new problem popped up. A new thought experiment that was considered by these four guys from Santa Barbara, Almeri, Maralf, Polchinski, and Sully, which I'll just abbreviate as AMPS. And this firewall paradox is what we're going to talk about in the next hour. This might be a very good time to stop. Yeah. So that one, it seems like complementarity is not enough to resolve that. And it's, again, a conflict between equivalence principle and unitarity. So let's take like 3 minutes, 4 minutes break.